All right, good afternoon. Thank you for joining us today. As we go through today, feel free to ask questions. In the Zoom interface, use the question and answer box um, to send in those questions, and I will do my best to answer them as we go ahead. Today's webinar is focused on, Wi-Fi 101, understanding, some of the what goes on behind the scenes to make Wi-Fi possible. Even though this technology has been around for nearly 25 years, there's a lot about it that people don't know, misunderstand, or is very counterintuitive. I've been doing this for a while, and even I'm still running across things that are new to me or challenge some of my previous ideas on how things worked. So we'll start here with just a simple slide, just a quick background on who Zyxel is in case you aren't familiar with us. We're a maker of computer networking equipment. We've been doing it since 1989, so we have over 30 years of experience making networking hardware. We have been making Wi-Fi products since the original 802.11 draft. Before there was 802.11 A, B, G, it was just 802.11, and we were making Wi-Fi products back then. We had our own chipset company that eventually got sold off to Qualcomm. We've got 100 million devices deployed out in the field, and our US office is based out of Anaheim, California. So now on to Wi-Fi, what you guys came here for. So we'll start by talking about three of the main players you're going to see when you start looking at Wi-Fi type equipment. The first one is the IEEE. This is the group that helps set the standards that for basically any sort of networking equipment. So when you look on data sheets for a switch or an access point, you will see a bunch of different IEEE standards there. So when you see things called such like 11AC, 11AX, 11B, those are referencing the standard that was created by IEEE. There's another group out there called the Wi-Fi Alliance. So the Wi-Fi Alliance came about initially to help market Wi-Fi to the end users, but they also then ended up stepping in and solving some problems. One of the problems we ran into with the IEEE standards is, language isn't perfect, and there's always different ways of interpreting the way things have been written. It's always possible, despite the months and years that go into creating and updating these standards, that things get overlooked that need to be specified. And then, of course, if there's nobody out there enforcing the standards, it's very possible for some vendors or some chipset makers to not follow the standards properly. So that's where the Wi-Fi Alliance stepped in by adding their Wi-Fi certified logo. So basically the Wi-Fi Alliance got together and said, hey, we need to solve some of these compatibility issues. We need to make things simpler for the end user. And they did that by creating their own interoperability tests required to pass in order to be able to put a Wi-Fi certified logo on your product. And you will generally see this on consumer equipment. You won't see it so much these days on business class equipment. Any product can call itself Wi-Fi. It does not have to be Wi-Fi certified to call it Wi-Fi, but it does have to be Wi-Fi certified to use the logo on the packaging. If you go to the Wi-Fi Alliance's website, you can search that for products. And again, you'll find most Wi-Fi certified products are more consumer or end user oriented, less technical oriented type products. The Wi-Fi Alliance is also the ones who decided to rebrand 802.11ax to Wi-Fi 6, 802.11ac to Wi-Fi 5, etc. And another thing that's kind of important here is getting that Wi-Fi certified logo changes over time. So for instance, for Wi-Fi 6, some of the features of Wi-Fi 6 were not required in order to be Wi-Fi 6 certified up until January of this year. And I think there are still a few features that Wi-Fi 6 has that are not necessarily required to be supported for the Wi-Fi 6 logo. So something else to keep in mind, a product certified today is going to have different features than a Wi-Fi 6 certified product, a year ago. And then last here is the FCC, the good old United States federal government. They are out there and they control basically the radio waves, and Wi-Fi uses radio waves to work. So the FCC sets rules as to what frequencies can be used, whether or not a license is required to use those frequencies, And they can set up other sorts of rules and testing that need to be done before you can import your product into the United States. So as mentioned just previously here, Wi-Fi works using radio waves. So basically the same things that apply to any other sort of radio wave apply to Wi-Fi. So as the frequency goes up, the more data can be easily fit onto the radio waves. But also as frequency goes up, the lower the range becomes. So a good example of this over time, for those of you that are old and ancient like me, is cordless phones. When cordless phones first came out, they were based around 900 megahertz. So the sound quality wasn't too great. The available unlicensed 900 megahertz spectrum is rather small. So you started running into some issues with these. Not only did you have call quality issues, but you had issues like if you lived in a condo or an apartment building, that you may be hearing your neighbors' conversations. On the other hand, you could walk really far away from your phone's base station and maintain a conversation. I was able to walk across the street to my friend's house with our phone, and it still worked fantastic. Then later in the early 90s, I think it was, 2.4 frequency opened up. So cordless phones moved to the 2.4 gigahertz spectrum, right? It's nearly 3 times the increase in the frequency over the 900 megahertz cordless phone. So what did that mean? It meant we got better sound quality. It sounded a lot better to be using your cordless phone, but because the frequency went up, the range went down. You know, you could no longer take that phone and walk across the street and be able to maintain a phone call. But you could probably still go out and walk around most of your yard. Then towards the mid 90s, they opened up the 5 gigahertz spectrum. So you saw a push to 5 gigahertz space. Again, sound quality went up, but the range became less. So those of you with giant mansions might have found that your cordless phones didn't even cover your entire house anymore, let alone allow you to go out into your yard and maintain a phone call. So same sort of thing going on here with Wi-Fi. Wi-Fi is using those exact same frequencies that cordless phones use. It's using, let's see here, it's using this 2.4 space. It's using the 5 gigahertz space. So one of the key things here is in order to be able to broadcast radio waves, in general, it's managed by the FCC and it requires a license. However, they have opened up these little chunks of spectrum for unlicensed use. So 900 megahertz, 2.4 gigahertz, and 5 gigahertz. And just recently 6 gigahertz, and we'll talk about that towards the end of today's presentation. But this is the frequency that any device that wants to use radio waves and doesn't want to bother the user with having to go out and apply and get a license from the FCC has to use. So these frequencies are shared by Wi-Fi, shared by Bluetooth, shared by anything that is wireless, is going to be using one of these 3 frequency bands, if not all of them. So that means we have to play nice and get along with other users and other types of devices that might be using the same frequencies we want to use for Wi-Fi. So now we'll talk a little bit about radio waves. So radio waves are measured in decibel milliwatts, similar to how sound is measured in decibels. And just like with sound, it is measured using a logarithmic scale. So for every 3 dB in gain you get, you are doubling the output power. So one of the things you'll notice when you're looking at Wi-Fi products is generally business class products will cite dBm. So radio output power will be measured in dBm, and they will also usually quote the antenna gain in dBi. So you can add the dBm from the radio to the dBi of your antenna, and that'll tell you the total output power that's being radiated out. Consumer products, on the other hand, tend to use milliwatts. And it's more of a marketing thing than anything else. At least that's how I believe it came about back in the day. So obviously, if you're going from 20 to 23 dBm and you're looking on a spec sheet, that doesn't sound very impressive. However, if you're looking at a spec sheet and you go from 100 to 200 milliwatts, well, geez, that's a huge increase in power. So that's what it was used to market towards the consumer who isn't necessarily very technically oriented. Meanwhile, over here on the business side, we stuck with DBM because you get more technical users. And until the last 5 or 6 years, it was very common for access points to use external radios, and for those, or excuse me, external antennas, and for those antennas to be removable and replaceable by the end user. So it was very important to use DBM so you could figure out what your total output power was. So it's very easy, like I said before, to take your radio DBM and add the dBi of your antenna to get the total output power. And for those of you that were doing outdoor deployments or doing more advanced indoor deployments, you would also be able to subtract out any losses from the lengths of cable that you were running, any of the connectors that you're using, et cetera, to be able to get a really good idea of what the output power was. Now, these days, even on the business side of things, it's become very rare to see external antennas on any sort of access point. So let's talk about some terms that are really important to know when you're doing Wi-Fi. One of them here is signal to noise ratio. Now, this is something that generally gets overlooked by a lot of people, but this is by far the most important thing you need to know when it comes to your Wi-Fi networks, the signal to noise ratio. Basically, how strong the signal that you want to hear is compared to any other signals or noise that may be in the environment. So basically, the higher the signal to noise ratio is, the better. And the signal to noise ratio is going to be what really determines how fast your Wi-Fi connection can work and the quality of that connection. This is going to be the most important thing to know when you're troubleshooting issues out in the field. Another common term here is attenuation, which is basically just a measurement of how much the signal decreases as it passes through different environments, including open air. So when your signal goes through an object, it degrades. So something like the air, it's going to degrade much slower than if it's going through something like a concrete wall, where it may not even be able to pass through the wall. So up here at the top of the page, we've got your formula. This is what you need to know to be able to figure out what sort of range you are going to get. So it's complex. And it's also why, again, another reason why dB is probably a better measurement of your Wi-Fi output power than using milliwatts when it comes to estimating something like range, because Wi-Fi range going from 100 to 200 milliwatts does not double your coverage area, not even close. And then we've got a chart here showing some common loss that you will see, or attenuation you will come across what's typical here, which you're going to find on some of these things here. So a standard window is going to give you around 3 dB loss. So just a glass window can drop your power by half, essentially. Tinted windows can drop it up to 8 dB. So huge drop. And that's because the metal on the windows will reflect and attenuate the signal more than just a standard window does. As you can see here, it makes sense. Basically, the thicker and more dense an object is, the more it's going to be able to absorb or attenuate your Wi-Fi signal. And Wi-Fi, particularly 2.4 gigahertz Wi-Fi, is particularly easy to be attenuated by anything that is got a large water content. So even when you are doing outdoor point-to-point links, if you plan it out during the winter and you test things and things work great, and then when it gets humid in the summer, you may find your performance declines. And that's because there's more moisture in the air, and the moisture attenuates the signal more than what you would have gotten initially when there was less humidity. So now let's talk a little bit about Wi-Fi range. And this is something that, again, tends to get overlooked by people, and that is that Wi-Fi is two-way communication. So the distance on which you can transmit is actually dictated by whichever device on your Wi-Fi network here is going to be the lower powered device. So it's very common to find access points, and I should have probably done dB here, but 500 milliwatt or higher broadcasting out of your access point, but your connected device is just a small amount, where or a cellular phone is probably at most 25 milliwatt, and many are much less than that. So since Wi-Fi is a two-way communication, the power of the weakest member is going to be the one that dictates what your range is, not the other way around. And this is why you will often run into these scenarios out in the real world where your phone shows it's got 3 bars of signal for the Wi-Fi network, but the Wi-Fi doesn't work or is just frustratingly bad. And that's because your phone is reporting how great the signal is coming in from the access point to the phone. It has no idea how much of its signal is actually able to make it back to the access point. Give me just a second here. I am being bombarded by messages. Okay, we're going to ignore those. So now let's talk a little bit about RF behavior. So, the problem with radio waves is they're invisible. There's no real way to see them. So it sometimes becomes hard to understand what they can be doing out there in the real world environment. In general, the best way to think about radio waves is to think about the type of waves that you can see, which would be like waves in water. So think about your deployment area as a pond, and think about whatever device it is that you have transmitting is essentially putting out waves in the water, similar to dropping a rock or a stone in the pond, and looking at how those waves disperse. It's very, very similar to what happens with radio waves. So you can see here your transmitter, the power goes out, and it radiates out for most devices in roughly a 360-degree pattern. And then it interacts with different things as it comes across them. So it is possible for our radio waves, unlike water waves, to pass through solid material. So you'll get attenuation, which will degrade the signal there. The signal also has the ability to go and wrap around objects, which is really interesting. It has the ability to hit objects and reflect off of them. And it also has the ability, when it hits something, when it reflects, to actually scatter and create multiple waves going out in different directions. So these are all things that, complicate the real world scenarios when you're deploying Wi-Fi and trying to troubleshoot issues. We often run into this in situations with warehouses or any sort of industrial building where there's a lot of electrical equipment, there's a lot of metal, because the radio waves can be bouncing all over those metal devices and creating problems. So another big problem we have here has to do with how do you handle multiple devices transmitting at the same time? The way Wi-Fi works, only one device can transmit at a time. Now, with some of the newer technology here, we have what's called MIMO, which does allow you to transmit to multiple devices to transmit at the same time. We'll talk about that a little bit later in other slides, but in general, when we're dealing with Wi-Fi and any other sort of RF environment, one device gets to transmit at a time. If 2 or more devices transmit at the same time using the same channel, it interferes with each other. For those of you that are old enough to remember, the cheap kids analog radio walkie-talkies, and you had more than 2 of them, you probably ran into this where you and one of your friends tried to talk at the same time, and your third friend just heard a horrible, nasty noise as the 2 transmissions interfered with each other. Same thing in general with Wi-Fi. So back in the early 802.11 days, we weren't doing a lot of streaming, we weren't sending a lot of data, and so this is what they came up with, is how to decide which device's turn it is to transmit. So basically, you had something to transmit, then you sense the medium. Basically, you listen and say, is anybody else transmitting? If somebody is transmitting, you then use a random number generator to wait, and you will wait that amount of time before checking again to see if they stopped. If you don't see anybody else transmitting, then you go ahead and transmit your signal. And then if somebody else does transmit at the same time, you get a collision and you back off and then you retry it again. So it worked fine for what it was, but it is a less than ideal scenario in the modern world where you may have, 50 or 60 devices connected to the same access point, and where you have people trying to send streaming data, doing voice over Wi-Fi, etc. We start running into issues and problems. And this is something that Wi-Fi 6 has helped solve, but plagues everything before Wi-Fi 6 and is still going to cause problems for your Wi-Fi 6 access point until all of your clients are also Wi-Fi 6 based. So we have another thing related to this called the hidden node problem. So we've got our access point here in the middle of the circle. And this blue circle is the range that this access point is able to cover. The yellow circle is how much range the mobile device has, in this case, a laptop. So you can see here, both laptops are within range of the access point. So the access point is able to hear or receive signals from both of them. The problem is they are not within range of each other. So when they go to sense the medium to see if anybody else is transmitting, they aren't able to hear each other. So even if one is already transmitting, the other isn't going to be able to hear it and know it's transmitting. It will go ahead and send its signal. And then your access point is going to end up dropping the packets because it's now got two signals coming to it at the same time. And it's going to cause interference and cause packet drops. So another term here to talk about here, I'm using the terms data rate versus throughput. The way I'm defining these terms is how I see it most often used out there in the real world. There are lots of variation on this, and not everyone is using it this way, but this is generally what you're going to see. So when you look at a data sheet for a Wi-Fi product, you will usually see a speed quoted. You know, it supports 300 megabit in connection. It's AC 1200, whatever. So that is what we're going to call the data rate. So it's also can be referred to as the physical rate or the link rate. And this is the total amount of data that can be sent over the Wi-Fi at a time. And what you will see often out in the real world, especially if you read Amazon reviews, is complaints about throughput. And people will go out there, they will test their Wi-Fi device and they will complain, hey, my throughput isn't even half of what you guys are advertising. You guys are, misleading people. You are lying to people. How dare you? And so what's going on here is people are generally measuring throughput versus the data rate. They are only looking at a small subset of the data that is being sent over the Wi-Fi network. Specifically, they are looking at the data they want. So a typical test on something like Ookla or speedtest.net or a command line utility transfers a file between two devices times how long it takes and says, here's what your speed is. So it'll take, we'll say, a 5 gig file, and it'll transmit the 5 gig file from one device to another device out on the network somewhere and say, here's what your speed is. So the only thing it is measuring is how long it takes to send that data, that file, between locations. What it doesn't take into account is all the other nasty stuff that goes on with Wi-Fi to make Wi-Fi work. Basically, again, Wi-Fi is using these radio waves in an unlicensed bit of spectrum that it has to share with any other type of device that is also using these same frequencies to do its thing. So because of that, it's a very noisy environment. It's an environment, as we just discussed, that's prone to multiple devices transmitting at the same time and packets getting dropped. So there's a lot of protocol overhead that goes into making Wi-Fi work. So when we're looking at the data rate, that extra overhead is included in what the data rate is, but it's not included when people do throughput testing, and that's where you see these issues. So because of that, it is very common to see up to a 60% difference between data rate, as I'm defining it here, and throughput as commonly being measured by end users. And so in general, even with Wi-Fi 6, it's a good rule of thumb is, any sort of speed test that you're doing is probably going to give you at best around half of whatever the advertised data rate is for that product. And this is something that's been used to measure speed claims or to make speed claims, since the very early days of computer networking, in large part because back in the good old days of Ethernet and coax cable and stuff like that, there was very little protocol overhead of the medium. Ethernet is largely just, sending the radio signals immediately. It doesn't have to have all this extra stuff that Wi-Fi has to make it work. And so that's why there's very little difference between data rate and throughput with an Ethernet connection versus with a Wi-Fi connection. So let's talk about increasing speed. How do we make Wi-Fi faster? So I'm taking a look at this not from you out in the field, but from a technology standpoint. Why is it that 11AC is faster than 11N? Why is 11N faster than 11A, et cetera, right? They're using the same radio frequency. So how do we make things faster? So one of the things we can do is what's called, encoding. How much data are we cramming onto those radio waves? So 11N use 64-bit QAM. 11AC, bump that up to 256 QAM, right? So we've quadrupled essentially roughly how much data is going in there. And then we quadrupled it again with 11AX Wi-Fi 6. We can now use up to 1024 QAM. So, why didn't we do this sooner? And the answer is basically it takes more horsepower to compress and fit all of this data, into these radio waves. So it's taken time for the technology to get to the point where you can do something like 1024-bit QAM on a mobile device and not kill the battery in just a couple minutes. So that's one of the reasons. Another thing that goes in here, as you increase the QAM, right, how much data you're cramming on there, the more important it becomes that you have a good quality signal and don't have issues. So one of the first things that your device will do if it's seeing that there's performance issues is it'll drop your encoding rate down to a slower one. So that's something you will very often see. If you've got a mediocre signal to noise ratio, you're not going to be able to get 1024 QAM on your Wi-Fi 6 device. It's going to automatically drop down to 256 or 64, whichever gives it the most reliable connection without issues. Because as you cram more data in there, it's more prone towards interference and failures and corruption of that data. The other thing is increasing spatial streams, and another one is increasing bandwidth. So increasing bandwidth is going from, say, 11G 20 megahertz channels to 11AC, which is using 80 or 160 megahertz channels. So we'll talk about this a little bit here. So we'll talk a little bit about bandwidth. So one of the questions that comes in is, why didn't you have Wi-Fi at 900 megahertz? And part of the answer to that is not only is it too low of a frequency, but there's not enough spectrum available. 2.4 was perfect for us. In that 2.4 has, in the US, 11 channels available. The problem is these channels are teeny tiny. They're around 5 megahertz, I believe, in size, whereas a Wi-Fi channel is using what's approximately a 20 megahertz channel. So the entire 2.4 gigahertz spectrum in North America only contains around 60 megahertz of available spectrum. So using 20 megahertz channels, what that means is you can have 3 different devices operating in the same area, and you won't have any overlap in the channel usage, so you won't have any interference. But as soon as you add a 4th device, it is going to overlap with one or more of the other devices, and it's going to start causing interference and start causing performance issues for you. So again, what we mentioned here, that one of the changes from 11G to 11N was we increased the available bandwidth from 20 megahertz to 40 megahertz channels. So we've doubled the bandwidth, essentially doubling the maximum amount of speed that can be, or doubling the amount of data that can be transmitted at a time. The problem again, though, is again in 2.4 gigahertz, there's only 60 megahertz available to be shared by everybody. So if you're using 40 megahertz channels, that means you can only have one device operating, and you try to add a second 40 megahertz device, it's going to cause interference. And even if you added a 20 megahertz device, the 40 megahertz channels are generally sitting right in the middle of that 60 megahertz. So you end up in a situation where it's always causing a lot of interference. So in the real world, it was very rare. You would either force 40 megahertz and just deal with the interference and hope that the interference is less than the double bandwidth that you have available, or you would have devices that you would set them to 40, they would see there's interference and they would automatically actually drop back to 20 megahertz operation without any user intervention. Just depends on whose product you're looking at, what algorithm they're using. So that was why there was a big push to 5 gigahertz starting with 11N. Because 5 gigahertz is a much larger chunk of spectrum. You've got something like 25, 26 non-overlapping 20 megahertz channels. right? So you can have a lot of different access points plugged in and operating in an area, and they won't cause interference with each other. But you'll notice here a good chunk of these channels are highlighted in this sort of peach color, and they're listed as DFS channels. So basically, what is DFS? So this 5 gigahertz chunk of spectrum used to be licensed spectrum. It could only be used by certain existing, it was previously only used by certain, licensed devices. The most common of which is radar, both weather radar or airport radar. So when the FCC said, hey, we're going to open this up and let anybody use this frequency, obviously radar operators and other people using legacy equipment that was using this spectrum said, hey, what about us? You're going to cause interference with us. We can't have the radar at the airport stop working. So DFS was the solution. So if you want to use this 5 gigahertz spectrum and use one of those DFS channels, you have to follow the FCC rules. So basically what happens is before you can transmit on a 5 gigahertz channel, you have to listen to it for a while and make sure there are no legacy devices using it. And then if there are none and you are transmitting and then you later detect a legacy device, then you have to stop transmitting on it. And then you have to change channels to a different channel. So this causes some problems for people out there because it can cause disconnects from the wireless network, right? So if it, you're broadcasting, you're connected, and your AP thinks it's hearing a legacy device, and it may not actually be a legacy user. It may just be some sort of RF interference from an industrial device that it thinks is a legacy device. It's going to disconnect you and either wait for that to stop or it's going to switch to a new channel. And if it chooses to switch to a new DFS channel, it can't do that instantly. It's got to stop and listen to that channel and verify that channel is not currently being used. So it causes user complaints, or has the potential to cause user complaints about being disconnected from the network at random times. And sometimes for, not a long period, but, for an end user, 5-10 seconds can seem like an eternity, especially when they're complaining to the IT department. Another problem with this is to get this DFS certification is it adds approximately 6 months to the FCC certification process. So especially when it comes to consumer products, where you're trying to get products out on the shelf first to be that first to market guy, a lot of consumer products never bother getting DFS support. So if you're in a situation where people are bringing their own devices into the office, or it's a hospitality environment or cafe where people are bringing in their own devices, there's a good chance some of your users have equipment that is not compatible with these DFS channels, and they'll never be able to connect. So for both of those reasons, what we see is a lot of people out there choose not to use these DFS channels. And obviously these are a huge chunk of the available spectrum. So you essentially go from 20 some non-overlapping 20 megahertz channels down to just 8 or 9 non-overlapping channels. So it's a big hit to the 5 gigahertz space that causes issues for some people and limits which channels people want to use for a lot of deployments. Now, of course, we're talking about here, how do we increase speed? Well, we increase the bandwidth available. So with 11N, we got to go up to 40 megahertz channels. As we talked about with 2.4, your 2.4 radio, only one device can be, basically operating on 2.4 before you have interference. With 5 gigahertz, if you're avoiding those DFS channels, you've got 4 non-overlapping channels to use, which is pretty good. Makes site planning pretty easy. But that wasn't enough. Everyone needs faster and faster. So we added 80 megahertz channels. Now you've only got 2 non-overlapping channels that you can use before you have to use DFS. So again, a lot of people aren't using DFS. So you start running into interference pretty quick in an office type environment or in a hotel or condos or apartments where you've got a lot of devices in the same area. And most Wi-Fi products by default will use the maximum available channel that technology supports. And with 11AC Wave 2, we went up to 160 megahertz channels. So if you want to use 160 megahertz channels, there's no choice. You have to use DFS. And with Wi-Fi 7, which is in the works, it's probably still at least for business class products, it's probably 2 to 3 years out. But Wi-Fi 7 is going to give us 320 megahertz channels to use. Is one of the ways that they're getting the faster speeds that Wi-Fi 7 is going to claim. Wi-Fi 6 is still using 160 megahertz channels. So the other technology here is spatial streams. So as we talked about before, you sort of, when you transmit, it's not a straight beam, it's a circular pattern that radiates out. It hits objects in the environment and bounces off of those. So that's what we would call multipath, because what happens is the same signal is taking multiple paths in the environment between the transmitter and the receiver. And because these paths are different lengths, it creates what's essentially an echo effect. So this used to be the bane of existence in the early days of doing Wi-Fi, was how do you deal with multipath? So what happened is some people eventually smarter than me realized that instead of treating multipath as a problem, multipath can be a benefit. And basically, as technology got better, we were able to differentiate the signal between the echoes. And then we were able to say, well, you know what? Because we have the ability to differentiate each of those echoes, we can use those echoes to send different amounts of data. So that's where we get a lot of the speeds we get today. So let's take 11N, Wi-Fi 5. A spatial stream with Wi-Fi 5, the maximum speed is 150 megabits. But by being able to use MIMO, multiple in, multiple out, and taking advantage of this echo type effect, we're able to send data simultaneously on the same frequency on 2 different antennas, knowing that those, because the antennas are offset, the paths that that signal is going to take are going to be slightly different, and we can differentiate between those two. So we can send different data on each of those and then combine them together. So when you buy a product that is an N300 device, that's telling you it has the ability to use 2 different spatial streams, send different amounts of data on each of those 150 megabit spatial streams, and then add them back together for a 300 megabit total speed. So if you saw an N450 product, that was telling you there were 3 spatial streams, so 3 different 150 megabit streams simultaneously. Now, the same technology was then improved with 11AC to what we called MU-MIMO, multi-user multiple in, multiple out. So in this scenario, we're still doing the same thing. We've still got the same spatial streams, but now instead of sending them to the same device, we can now use 1 spatial stream for one device, 1 spatial stream for another device. So the aggregated throughput is still 300 megabits of data in a 2 spatial stream scenario, but it's 150 megs for each one of these users. So this is how we start getting to the ability to do multiple devices transmitting at the same time, is taking advantage of our ability to identify multipath and segregate those signals at the chipset level. So with 11AC, we only have what was called downstream MU-MIMO. Your access point or your router could transmit to multiple devices, but your end users still had to take turns transmitting back. And if 2 or more transmitted at the same time, you got interference. With Wi-Fi 6, we now have the ability to do multi-user MIMO in both directions. So now we're finally at that situation where multiple devices can transmit at the same time by using different spatial streams from each other. But again, the overall speed for each user is going to be less. So your aggregated throughput is going to have to be divided by the number of users. And I think with Wi-Fi 6, there's a maximum of 8 spatial streams. If you had the most high-powered Wi-Fi 6 device, most Wi-Fi 6 devices, there are only 4 streams, 4 spatial streams. So you have to split that up between your users. So when you're looking at the data sheet, again, when it comes to business class equipment, you oftentimes will not see a speed claimed at all. You won't see an N300 or an AC1200 or whatever. You will just see 2.4 gigahertz radio is a 3x3 spatial stream. A 5 gigahertz radio is 4x4 spatial streams. So that's telling you how many spatial streams you support. In general, when it comes to access points and routers, both numbers will be the same. So the first number is how many spatial streams you can transmit. The second number is how many spatial streams you can receive. So again, most of your APs and routers will be 2x2 or 3x3 or 4x4. It'll be the same number. But when you start looking at client devices, the Wi-Fi that's built into a tablet or a mobile phone, you will see a difference between those numbers. You will see 1x2 or 2x4 or something like that. Generally, these mobile devices have the ability to hear and listen to multiple spatial streams and combine them together, but they are not able to transmit as many spatial streams back to the access point itself. So you end up in a situation where they're able to receive, say, 350 or 300 megabit connection, but when these send data themselves, they're only able to reach 150 megabits. This also comes back to our throughput versus data rate discussion, because what that means is when you're doing your speed test is not going to be the maximum because your client device itself cannot support the maximum speed in both directions. Now, there is one exception to this rule. You will sometimes see, Cisco is probably the one that's most guilty of this, something like this here. I know it's small. It's 4x4:3. So at first you may say, hey, well, that's 4 spatial streams. But no, that number after the colon is actually how many spatial streams it supports. So even though it says 4x4 here, it's actually only 3x3 in practical usage. So why do they do this? So some vendors, instead of using smart antenna, will do this. It was really popular in the early 11N days. And basically the idea was, well, we have 4 antennas or 4 spatial streams that we can choose to use. But our horsepower can only support 3 of them, so we'll choose the 3 best. So in theory, you've got 4 antennas to choose from, but you can only use 3 at any one time to either listen to or create different spatial streams. So again, the important number when you see the colon is basically going to be the number after the colon. So putting it all together, the maximum speed you're going to get to is going to depend on how many spatial streams are supported, which modulation is being used, and how wide the channel is. So when you look at products here, like for something here that calls itself AC 900, the maximum actual data rate is 866. It's rounded up to 9, and it's assuming that you can support 160 megahertz channels, 256-bit QAM, and 1 spatial stream. So obviously, in the real world, unless you're really close to your access point, you may not be able to achieve all of those. You may only be able to use an 80 or 40 megahertz channel, for instance, due to interference issues. It may be due to low signal to noise ratio. You can't use 256 QAM. You can only use 64-bit QAM. So it gets kind of messy here. And again, that goes back to the testing an end user will do. What is the actual RF environment that they're testing in? And how much is that maybe degrading the quality of the signal or the maximum speed that they would ever be able to achieve? So now another question we get a lot is, well, how many devices can I get on this access point? And in general, the number that you see on that data sheet means absolutely nothing. You will see people claiming 256 users per radio, 512 per radio, 1,024 per radio. In general, you will never even achieve the lowest of those in the real world before your Wi-Fi network starts having issues. And it has nothing to do with the access point hardware itself or the router hardware itself. It has to do with the Wi-Fi standard and the types of traffic that we are doing. So, we're having to divvy up the signal that's out there. And as we talked about, the ability that we determine whose turn it is to broadcast is really, in a modern scenario, is really poorly implemented for how the modern users are using Wi-Fi. So you run into hidden node problems, which cause interference and packets dropped. You run into situations that's not technically hidden node, where 2 or more devices decide to start broadcasting at the same time. And then if they do detect someone's broadcasting, you're using a random number to determine when it's your next chance to try to get in there. So there's nobody coordinating which user gets to transmit at once. And it turns into a free-for-all. And basically, as you add more and more users to a access point or a router, the aggregated throughput's going to go down. And as you add more and more devices, the more interference you're going to run into, the more packet drops you're going to have. So in general, you are going to run into these Wi-Fi, just general Wi-Fi standard mechanic issues long before you get to whatever the maximum number of users listed on the data sheet is. That data sheet number is basically just how much memory is dedicated to the allocation table. Has nothing to do with real world performance. So, and switching from one brand of AP to another brand of AP that are the same Wi-Fi specs, even if the data sheet changes to how many maximum users you have, realistically, it's not going to make any difference out there in the real world because the AP isn't the choking point. The choking point is just the Wi-Fi standard and how it works itself. So we've got a scenario here. So this is just looking at here. We've got users. These users are watching a 3 megabit per second YouTube stream. So I think that's what, 480p, 720p, something like that. So it's a 3 megabit stream in this scenario. And so what we've got here is we've got a laptop. The AP supports 3 spatial streams. The laptop supports 3 spatial streams, at least on the receive side. So what you can do is you can get 34 laptops on that network, all of them downloading that 3 megabit stream with no issues. You get an aggregated throughput in this scenario of 100 megabits per second. Now we swap out these laptops with a tablet, and we're assuming the tablet is the same output power. The only thing that is changing in this hypothetical scenario is the number of spatial streams that the client device is able to support. So by dropping to 2 spatial streams, aggregated throughput drops from 100 megabits per second to 65 megabits per second, and you can only fit 21 users on that same AP before you start running into issues. Same thing, we'll drop it now down to 1 spatial stream. Now you can only get 10 devices onto that same AP, and you only get an aggregated throughput of 30 megabits per second. And then obviously in the real world, not only do you have different users with different numbers of supported spatial streams, you've got users with different signal strength. You've got some users that are using Wi-Fi 6, some users are Wi-Fi 5, some users are Wi-Fi 4. So you've got all of these different scenarios out there that are going to degrade the number of users on there. None of which have to do with the access point itself. It's just the unfortunate nature of Wi-Fi. So, how many users you can fit on there just depends on what you are doing. In general, you would look at, how much bandwidth does each need and, divide that up. And that's how many users you should have on your network. But there are exceptions to that. The big one being people trying to do voice. So the great thing with streaming a movie or video off YouTube is you can buffer that. You can buffer it. So if there are any sort of performance issues, it doesn't matter. There's a half-second or 3-second buffer. So if data comes in out of order, if packets get dropped, it can be reassembled in the right order before it's displayed for you to see. But when you're talking to somebody, you don't have the ability to do a buffer, because if you do a buffer, it adds delay and it makes it really hard to have a conversation because you end up each cutting each other off. And we've all run into that doing, conference calls and things like that where they're using VoIP, where you get that echo or that delay where, similar to Wi-Fi devices, right, where you're waiting for people to stop talking so you can talk, and then 2 or more of you maybe decide to talk at the same time. And there's a slight delay, so you both don't know it until you're, partway into your thought. So it's the same thing with Wi-Fi, especially with doing voice over Wi-Fi, because it is so sensitive to jitter, it is so sensitive to latency. So even though there's not much bandwidth used, the typical, voice communication is under 100 kilobits per second. It's teeny tiny. But because of that, you can't have too many users on an AP doing voice at the same time, because of the drop packets and other issues with Wi-Fi will start causing jitter and increased latency, which makes having a conversation difficult. So again, you've got to look not just at bandwidth, but what the actual application is. And that's why voice over Wi-Fi is so hard to do and make your users happy. So now I want to talk a little bit about co-channel interference and smart antenna technology. So what is co-channel interference? It's basically 2 or more devices broadcasting at the same time. I've talked about it over and over, so I'm not going to explain it more for you. Now, your typical way of dealing with co-channel interference was, you would carefully plot out where you're putting your access points and then choose the channels you were using carefully to try to keep APs on the same channel from being too close to each other. But as you saw, as we increase speeds by increasing bandwidth, you start ending up into interference situations anyway. And then if it's something like an office building with multiple tenants and you're only equipping one of the tenants, you have no control over what the neighbors are doing. So the way that we would traditionally handle this, and we still do recommend this in some situations, is turn down the transmit power. Right? As we talked about before, your AP is able to output a tremendous amount of power, but your client devices can't. So the signal from the AP goes much further than the signal from the client devices. So if you turn down the power, you probably aren't hurting your range too much, but you're decreasing the amount of interference between the different access points. Now, the challenge with this, though, is you decrease that power, you lower your signal to noise ratio. So you're trading one thing for another. You're trading drop packets for maybe slower overall speeds, but more consistent. So it's a trade-off. And again, there are situations where we do recommend you drop the power of your APs. A better solution to this is smart antenna. Now, your typical AP has a fixed antenna pattern, and it's been designed to be mounted on a ceiling directly over the area that's being covered. Smart antenna, on the other hand, is something that's really nice. We offer it on many of our APs. Ruckus, if you've bought or you're familiar with Ruckus and their BeamFlex is smart antenna. Their BeamFlex Plus is probably closer to our smart antenna implementation. So basically what happens with smart antenna is you've got an array of antennas built into the access point. And they're able to scan through a lot of different antenna configurations to choose the antenna configuration that focuses the power towards where the client is and ignores other sources of RF interference. So our algorithm puts a lot of emphasis on finding sources of RF interference. So most of our APs can do up to 700 different antenna patterns. So you've got a lot of antenna patterns in there to choose from. And the update nearly real time. It doesn't require anything special on the client device. And unlike beamforming, it doesn't require the client device be stationary. Smart antenna works on mobile devices. So we're able to change the antenna pattern as the client moves around in the environment. And we use a different antenna pattern for each individual client device. So what this does is it solves a lot of the co-channel interference issues between different devices or different access points. So it makes a huge difference on performance in dense Wi-Fi environments. That could be situations where you have a lot of APs in the same area or where you have a lot of users on just a small number of APs, where anywhere there's a lot of RF transmission going around or other sources of RF noise, smart antenna makes a huge difference. It also works really well in warehouse environments where the RF environment's constantly changing as shelves fill up and unfilled and stuff like that. So smart antenna works really well in those type of environments as well. So here's an example test we did. In this one here, we are in a hotel environment. This is one of those using the low-powered wall plate APs where each room is getting its own wall plate AP. The test is being done in the 5 gigahertz. So 5 gigahertz gives us a lot of different non-DFS channels to choose from. And it also limits how far that signal goes because 5 gigahertz isn't very good at penetrating through solid objects. And we made sure that when we're laying things out, there are no APs directly next to each other using the same channel. And this is a 2-floor environment. So we've also made sure there are no APs using the same channel directly above or below each other. And we've taken 2 products here for our testing. We have taken a Ubiquiti product and a Zyxel, the NWA 1302, which is EOL. Replacement, similar modern model would be the NWA 5302 D-SV2. But anyway, the important thing here is us and the Ubiquiti on paper are pretty much the same configuration, the same form factor. The primary difference between us two is the smart antenna technology. So with a single AP, you see here, it's basically the same. Ubiquiti, in fact, beats us by a teeny tiny amount on aggregated throughput, 406 megabits versus 404. So smart antenna does nothing in this scenario. But now when we turn on a second AP, again, not directly next door to it, using the same channel, we start to see where smart antenna makes a difference. So what you see here is if you aggregate the throughput between both APs, with Zyxel, you're getting 785 megabit per second aggregated throughput. With the Ubiquity, you're getting 555 megabit aggregated throughput. So that's a pretty significant jump in aggregated throughput to be shared by the users. And what's interesting here is if you look at the theoretical channel utilization, right? They're both using the same channel, so they, in theory, have to share that airtime. And in theory, the maximum should be 100%. And what you see with Ubiquity is they're using 95% of the available airtime on those channels and split between the two. We're able to achieve 131%, 31% more airtime utilization than in theory is possible. And that's because of the smart antenna. Basically allowing these devices to ignore each other and not listen to each other. So they're not getting the overlap that you would normally get. So now we add another AP. So this is the third AP. And again, they're not next to each other. They're not above or below each other. They do have spaced out space here, but we see in this scenario, same thing. Now we've got an aggregated throughput of over 300 megabits per second, where the Ubiquity is still under 600 megs aggregated throughput. And what we actually see here is our airtime utilization has increased to 155% of the theoretical maximum. Ubiquity's has actually dropped to 91%. And that's just because they're getting more interference, so they're getting more packet drops. It's less efficient utilization because of these interference issues of the available airtime. Another thing to note is if you look at our APs, each of them are getting around 300 megabits of data allowed through each AP. Where you notice here on the Ubiquity, it's very non-standard, very non-uniform. You get 286 on one AP. One AP is only getting 80 megabits per second. The other is getting 178. And again, this is where the smart antenna is helping reduce the interference between devices. So they're not fighting each other for the same airtime. They're able to use the same channel at the same time without interfering with each other. So we've got some other technologies out there that we use. Obviously, not everyone has the money or the need for smart antenna. So out in the real world, again, most APs are designed to be mounted on the ceiling. They have one fixed antenna pattern. But in the real world, you often run into scenarios where for whatever reason, you cannot mount the access point on the ceiling. You need to mount it on a wall. And when you do that, obviously you're taking an antenna pattern that's designed to be mounted above devices directly below it. You put it on the wall and you end up getting a less than ideal coverage pattern. You end up sending a lot of the signal up into the ceiling, down into the floor, and it's either being lost or in the case of a multi-story building, maybe causing interference to your neighbors above or below you and their access points. So our solution for this was something called dual optimized antenna. So we've got certain products that come with dual optimized antenna. And basically they've got two antenna patterns, one that's optimized for ceiling, one that's optimized for wall. And we allow you to switch between the two. So you can deploy this one AP and use the same AP for both ceiling and wall mount deployments. You just either flip a switch on the device when you install it, or you can always log into the device and change which antennas it's using based on where you've installed it at. So that's one of the ways we help solve that issue is dual optimized antennas. And for the most part, you will find that in our 5 and 6 series products. So just some general rules here when it comes to doing installation. Again, most APs are designed for a ceiling mount directly over the area to be covered. You don't want to install them on a wall if you can avoid it. If you do have to install them on a wall, you want something with dual optimized or smart antennas. And in general, basically, the higher the AP is above the area being covered, the better. And the reason for that is really simple. You're trying to avoid attenuating that signal. So by mounting it up high, it makes it easier for that signal to avoid, obstructions. Humans, cubicle walls, shelves, copy machines, things like that. So you want the signal to be able to transmit through as much clean air as possible between the device and the access point. So as higher is better in general within reason. Obviously, if you're in something like a basketball stadium or something like that, which has got really high ceilings, you may not want to mount it that high because the signal will radiate out and become too wide of a coverage area, maybe causing interference. The signal's having, even though it's open air, it's still having to travel much further than it should need to. So you may be getting some attenuation there, etc. When mounting it up on the ceiling, some things to keep in mind is, take into account what's on that ceiling. So it's very common in a lot of industrial buildings where the actual ceiling is really high, and on that ceiling is ductwork for the AC system. There may be metal conduit for electrical, there may be piping for sprinklers or for things like that. So again, anything that's metal, anything that's solid is going to cause interference issues. So if you're mounting on those types of ceilings, you want to try to find an empty spot that doesn't have those type of obstructions nearby, or you may want to drop the AP down on a extender so it sits below the obstructions. And of course, in a lot of scenarios where you've got those high ceilings, you've got a lower drop ceiling, an acoustic drop ceiling. And you know what? It's perfectly fine to rest the AP on top of the drop ceiling, provided your local building codes allow it. They may or may not. So you need to know that, whether you can mount them above the drop ceiling or not in the plenum space. But it absolutely works. The typical drop ceiling acoustic tiles have very little attenuation. And we have had a lot of customers say, well, my end user who's paying me to install this, they don't want me to drill holes in the drop ceiling. They don't want me to run a wire through the drop ceiling. They want me to leave the drop ceiling alone. So in those scenarios, just rest it pointing down on top of the drop ceiling. It should work. Place it in the center of the acoustic tile. You don't want it over near the metal T-bars that hold those up. Again, you're trying to avoid metal because metal causes all sorts of interference issues due to reflections and stuff like that. But that is an option if it is allowed where you are. So we'll talk a little bit here about hotels. So the traditional way of doing things has been what we call umbrella coverage. Generally, you would mount the access point in the hallway, and that access point would cover anywhere from 4 to 16 rooms, depending on the access point being used and the construction of the hotel itself. And what we're seeing is that's largely going away, at least on most of your, I don't know what tier you want to call it, your Hampton Inn and higher, your Holiday Inn Express and higher, that sort of business class motel and higher. What we're seeing a move to here is individual APs per room or per every other room. In particular, those wall plate type of APs. So, question is, why are we seeing the move from umbrella to this? And there's a couple different reasons. A main one is just, what people are using Wi-Fi for is different than what it used to be. It used to be, someone would come in and they would have, their laptop, and they would use their laptop to send emails or check a website. So it was short, bursty traffic. Nowadays, people are wanting to be able to stream music, stream video. Heck, even if you are just trying to read some news stories, a lot of websites have autoplay advertising videos running, whether you want them to or not, which all require more bandwidth access. So you've got that. You've now got the case where, compared to before, you've got more users. You may have your laptop, you may have a tablet, your laptops for work, your tablets for watching Netflix, and you want to get your phone onto the Wi-Fi because the 5G signal is poor where your room happens to be. So you end up with one user with multiple devices on there, and then you multiply that by 4, 8, or 16 rooms, and suddenly your AP is getting kind of overwhelmed. And then the other part of it is we've moved to 5 gigahertz. So the 5 gigahertz doesn't penetrate walls very well. And in a lot of hotels, the room that's closest to the hallway where your AP is the bathroom. So you've got thick, dense tile bathrooms, you've got pipes in the walls, all sorts of things which cause issues. So for all of those reasons, we're seeing a move to 1 AP per room. Another main reason for this is we're seeing a lot of hotels where the TV and the phone is being done over IP. So now you run one Cat5 cable to the room, it plugs into your wall plate AP, and then your wall plate AP has pass-through ports, including PoE pass-through. So you can use one cable to the room and then run cables from that AP to the IP phone to provide the phone service, and to your TV set-top box so it can provide IPTV to the room. So a lot of newer constructions, instead of running the, separate cables, a coax for the TV, Cat3 for the phone, Cat6 for your internet connection. Now they just run one Cat6 and save themselves from having to drop all those different types of cables. So if you are mounting in a room, some things to keep in mind. Generally, you want some sort of mounting plate that isn't obvious how to remove it, because people will steal anything they can from a hotel room. So you want to make it harder for them and require them to, at least know something secret though. So like for most of our APs, when we mount them, to unlock them, you have to use a pen or a chopstick and shove it in a little hole to cause the release. So your typical guy who's just looking to conveniently grab anything in the room as he's checking out isn't going to be able to steal the AP. Another thing is to look at is the ability to turn off the LED lights, because no one wants an AP above their bed blinking at them while they're trying to sleep and they're all jet lagged. And yes, that is something we have gotten end user complaints about in the past. So most of our APs, you can turn off the main LED lights on them. When it comes to the public areas, you're going to want to deploy based generally on user density, and you're going to want to plan for each area independent. So you're going to plan the lobby separate from the lobby bar, separate from the attached restaurant. Treat each of those independently. And in general, the more users you will expect to be using the internet in those areas, the more APs you need to use to cover it. So, the hotel bar may just need one because very few people are getting on the Wi-Fi in the bar. The lobby may need a few because, in the early morning when everyone's waiting for everyone to wake up and finish their breakfast, you may have a decent number of users who want to get on the Wi-Fi. And then if you have a conference room, you may need more APs than you would initially think. Even though the area may be small, you may have 30 or 40 users at a time all trying to get on the network. So you may want to put in more APs to help distribute those users across them. And again, you want to use load balancing and client steering. And again, this is a key one here. You want to do this by the area. We have had some of our partners, try to do load balancing across the entire hotel as one big zone. And that just doesn't work. So you want to set up different zones and do your load balancing and treating each one of those different zones independently. You don't want the guy on the 5th floor. You don't want the AP going, well, I'm kind of heavily loaded. Let me push him to this AP that's not being used, which is down in the lobby where they're not going to be able to connect to it. So you want to set up zones based on the physical locations of the APs when you're doing client steering and load balancing. And again, anywhere where you've got a lot of users or a lot of devices, think about using smart antenna. So school strategies here, same sort of thing. You need to ask yourself, how many students are going to be in this room, and does each student have a Wi-Fi device? So some classrooms, they may not use their Wi-Fi devices. You may be able to get by with just one AP. If it's one of those things where every kid has a tablet or a Chromebook and they're all getting on the network to do their tests, you may need to add additional AP to handle that many number of users. And if they're doing something like where the teacher, instead of using a whiteboard, streams simultaneously to every single user in there, you may need another AP than you would have think because of how much bandwidth is being used, since Wi-Fi doesn't really do multicast all too well. And most of these systems I have seen are doing unicast to each individual student's screen, not multicast. So things to keep in mind. In general, you want to do, for classes of 20 students or more, 2 APs per room. And if you've got 30 or more students in the room, we highly recommend you use smart antenna. Keep the teachers and the students on different VLANs. You don't want them accessing the same network or being on the same network directly. And then using firewall rules or switch VLAN rules to, control access to shared resources that both the students and teachers need. So now we'll talk a little bit about Wi-Fi 6 and Wi-Fi 6E, but we'll start with 6. So Wi-Fi 6 was initially was being marketed as high efficiency wireless, and then the Wi-Fi Alliance rebranded it as Wi-Fi 6. It is also known as 802.11ax or just 11ax. These are all the same things. So it was specifically designed as one of the first major overhauls of the way Wi-Fi works, and it solves a number of the issues that we've been running into with Wi-Fi. So by able to do upstream MIMO, you now have the ability for multiple users to transmit at the same time without causing interference with each other, at the trade-off that each user is getting a slower speed at the time. You've got something called BSS coloring. So it reduces interference between APs in the same area by being able to tag the traffic as to who it's intended for, so it can be safely ignored if it's not intended for you. We've got improvements for how devices determine if it's their turn to broadcast. So it allows you much more efficient utilization of the airtime. So what you would see with a typical 11AC product is as you add more users, the airtime utilization actually goes down and the aggregated throughput goes down. But with Wi-Fi 6, as you add more users, the aggregated throughput remains the same. So it makes a big difference there. So it solves, or it's designed to solve many of the same issues that Smart Antenna solves, but it's going about it in a different way. And because of that, it's complementary. So Wi-Fi 6 will give you improvements over Wi-Fi 5 in these dense environments, but Wi-Fi 6 with Smart Antenna will do even better than just regular old Wi-Fi 6 because we're solving some of the same issues, but in a different way, and they complement each other. So, you know, the IEEE group has been working on Wi-Fi 6 for a long time. It wasn't officially ratified, I believe, until Q1 2021, even though there have been products on the market advertised as Wi-Fi 6 long before then. So what you will see is a lot of these first generation chips are missing some of these key features. So they're calling themselves Wi-Fi 6, but they may not have all of the Wi-Fi 6 feature set. Something like upstream MIMO, the ability to do multiple users transmitting back to the AP at the same time, it wasn't added to the Wi-Fi Alliance's certification testing until January of this year. So you can be buying a product that launched August last year. It's maybe Wi-Fi Alliance certified, but it may not support some of these newer features or some of these features such as upstream MIMO. So something to keep in mind. And it can get confusing when you are looking at Wi-Fi 6 product. And it's not, you know, we used to like to say, well, it's just the old stuff. So if you look at a product and it launched, you know, initially launched 2 years ago, avoid it. It's probably using one of these first gen chips. But what we have seen is we have seen some products that have launched fairly recently that are using these old Gen 1 chips, in part because it's cheaper than the Gen 2 chips, and in part because they tend to use a different production process than the Gen 2 chips. And so because of that, they aren't as subject to as much of the IC shortages that are plaguing our industry right now. So it's easier to put products out on the market if you can actually get a hold of the chip, and it's easier to get a hold of these Gen 1 chips. It's just you may be missing some of these key features, and these key features I tend to think personally are something you want because they make a huge difference and will as far as future-proofing your network. And without them, you're missing out on a lot of the benefits of Wi-Fi 6. Another key thing here is Wi-Fi 6. It improves both the 2.4 and your 5 gigahertz radio. 11AC only improved the 5 gigahertz radio. So some vendors, including some of the Ubiquiti product, are only putting Wi-Fi 6 on the 5 gigahertz radio. That 2.4 gigahertz radio is still using Wi-Fi 4 technology on the 2.4. So that's another thing to look at when you're looking at products is, does it have some of these advanced Wi-Fi 6 features? And if it does have them, are they available on both radios, or is it only on one of the two radios? So when it comes to Zyxel equipment, any of our business class APs, which are those with 3 or 4 digits in the name, those all are using full Wi-Fi 6 feature sets, and it is across both of the radios. We have some prosumer stuff, the NWA 50AX, and the soon to launch NWA 90AX and the NWA 55AXE. Those are using, it's a newer chipset, but it doesn't support all of the Wi-Fi 6 features. I prefer to refer to those as Wi-Fi 6 Lite. However, unfortunately, other vendors in the industry are not using that naming. They're just calling everything Wi-Fi 6, regardless of which features are being used or which radios support it. So just keep that in mind. Everything, NWA 110 and up has the full Gen 2 chips, the full feature support, and it is on both radios. So there's something called Wi-Fi 6E. We expected to see a lot of products with it last fall, but because of the IC problems, we didn't really see much hit the market until this year, and it's still just slowly trickling in. So what happened here is FCC opened up some new spectrum for us in the 6 gigahertz space. Right, so before we had 2.4 and 5, now we have the option to use 6. Wi-Fi 6 can function on these frequencies. So devices that support the 6 gigahertz frequency will be marketed as Wi-Fi 6E. Now this unlocked a huge amount of RF spectrum. This 6 gigahertz spectrum is 1.2 gigahertz in size. So it's gigantic. It allows us to have 7 non-overlapping 160 megahertz channels. So you don't have to worry about interference, even if you're using the maximum data rates, because you can have 7 different APs operating, each of them on a non-overlapping channel at full speed, no issues. So that's good. There are problems though. So you need to be aware of some of the pros and the cons. So one of the cons is obviously frequency's gone up. So range has dropped down. And that is, if you look at a lot of the consumer equipment that's out there that was first to market with 6E, that's the complaint. You don't get the range. And if you got a bigger house, you're not being able to use the 6E radio, very far from your AP. So that's one of the challenges we run into. Another challenge we run into here is people were using this 6 gigahertz frequency before the FCC decided to allow unlicensed users to use it. So we run into a situation like 5 gigahertz, where with 5 gigahertz, we had DFS. With 6 gigahertz, we have automated frequency control. So that's what's being used to try to stop the interference between older legacy devices. So those older legacy licensed devices still are getting priority. It is less intrusive than DFS was. So it shouldn't cause as many problems as DFS did. But unlike 5 gigahertz, where DFS is only a subset of the channels, automated frequency control is across the entire 6 gigahertz spectrum. And I may be wrong on this, but I believe it's only for outdoor stuff, which leads us to another problem. We're still waiting on the FCC to finalize the rules for outdoor Wi-Fi 6E use. So while it is possible to buy Wi-Fi 6E indoor product, at the moment, it is outdoor product. We're still waiting on the FCC to figure out how to get product tested and certified for that. Another challenge we may run into with Wi-Fi 6E is some products will have 3 radios, a 2.4 radio, a 5 gigahertz radio, and a 6 gigahertz radio. But some products will only have 2 radios, a dedicated 2.4 radio, and then 1 radio which can operate either on 5 gigahertz or on 6 gigahertz. So that will be something else to keep in mind when you're shopping for a Wi-Fi 6E device, as you will need to check, am I able to use all 3 bands simultaneously, or am I only going to be able to use 2 bands? And if I'm only able to use 2 bands, do I really want to use Wi-Fi 6E, or should I just, because of the range issues and whatnot, do I want to just stick with 5 gigahertz and then maybe buy a cheaper non-Wi-Fi 6E product? So it's something to keep in mind. And one thing to be keeping in mind when you're shopping is, does this support 2 or 3? Obviously, another challenge with supporting such 160 megahertz channels simultaneously with 160 megahertz channels on 5 gigahertz is that you need a lot of horsepower to handle the bandwidth. So that's going to be another challenge here. A 3 radio Wi-Fi 6E solution is probably going to be very expensive, because not only are you paying for 3 radios, you're paying for a CPU which can handle the throughput of 3 radios, 2 of which are really, really fast. So just things to keep in mind. I still cannot tell you when Zyxel will have Wi-Fi 6E. It is something we are actively looking at and watching, and do plan to have product in that space. The idea, though, is we will launch an entire family on the same platform. So we need the outdoor stuff to get settled, the indoor stuff to get settled, and for the chips themselves to have the full feature set that we want to support. We don't want to roll out a chip that's missing features. So with that, we've finished up today's webinar. I did mention there is Wi-Fi 7. So Wi-Fi 7 is coming. Wi-Fi 7 allows 320 megahertz channels instead of 160 megahertz channels. It has some other improvements planned. You may see some consumer equipment, which is partial Wi-Fi 7. So they'll advertise themselves as Wi-Fi 7, maybe at the end of this year. Although I think for business class product with the business class features, multiple SSIDs, VLAN 2, VLANs, things like that, we're probably looking 2 or 3 years before those start hitting the market. And again, just like with Wi-Fi 6, to take advantage of those features, you will need your client devices to also support those features. And client devices generally tend to lag on the features even further behind the consumer equipment. So things to keep in mind. So all of our webinars, or most of our webinars, are recorded. You can find them on our YouTube page. Our YouTube channel here is Zyxel America channel. So if you've missed one of our webinars, feel free to check it out there. If you want to share today's webinar, you will find it there in the next day or two. And then we're also on LinkedIn as Zyxel US channel. If you have any questions, send them in. I have not received any as we've gone through today. While I wait to see if anyone sends them in, thank you for joining us. We've got more webinars planned this month. Be sure to check those out. Feel free to email me directly, seanr@zyxel.com, SHAWNR@zyxel.com, with feedback, suggestions for different webinar topics you would like, mistakes I've made that I should correct before I do this presentation again. Feel free to email me directly with those. And then we do also have our user forum, forum.zyxel.com. It's an area for Zyxel end users and installers to be able to get help from each other. It is also, though, where our HQ posts up security notices, release notes, things like that. These show up there first. And we do have our R&D and PM team monitoring those. So you will see them jump in from time to time to answer questions. And they do monitor that to get ideas for feature enhancements for future products. Okay, I haven't seen any questions come in, so I'm going to go ahead and end today's webinar. Again, thank you for joining us today.